Hello everyone, my name is Bara Muhammad, and today I will explain the ALU design for RISC V CPU. And I want to thank my group members Nuruddin Ahmed and Ahmed Shukri who contributed to this project. What is a RISC V? It is an Open Standard Instruction Set Architecture, or ISA. Unlike proprietary ISAs like those from Intel or ARM, RISC-V is free and open source, which means anyone can use and modify it. It's designed to be simple and efficient, making it suitable for everything from small embedded systems to high performance computing. Some of the key features for RISC-V are that it is modular, meaning you can add or remove features as needed. It's also scalable, so it can be used in a variety of devices, and it's simple, which improves the speed and reduces power consumption. So, what is an ALU? ALU, Arithmetic Logic Unit, is a critical part of the CPU that handles all arithmetic and logical operations like addition, subtraction, and comparisons. It acts as the brain of the CPU's mathematical and decision-making processes. For example, when the CPU needs to calculate the result of a math problem or check if one value is greater than another, it's the ALU that gets the job done. The operations may seem basic, but they form the foundation of every task a computer performs, from running applications to processing data. In the ALU diagram, the specifications for it are the inputs A0, A1, A2, A3, B0, B1, B2, and B3 are 4 bits each. B underscore SEL and A underscore SEL are 2 bits each. ALU underscore OP, clock, and reset are 1 bit each. The output is ALU underscore out, which is 4 bits. When the ALU underscore OP becomes 1, the operation becomes a 4-bit adder. When it is 0, the operation becomes a 4-bit subtractor.
Assalamualaikum, my name is Ahmad Shukri bin Shamsul, also part of Group 3, and what's shown in front of you is the ALU design that we have created using Quartus Prime software. So for now, we are going to explain the most important part of this ALU, which is the ALU adder and subtractor partition. There's also the part where it accepts multiple inputs, and also the final part, which is the D register, which is going to produce a final output at each clock cycle.
In order to make up the addition and subtraction unit, we must first start with a full adder.
Our value for A is 1, and our value for B is 1, and our value for the carry in is 0. So when A and B goes through the XOR gate with a value of 1 and 1, we know the XOR only accepts different inputs. So we have 1 and 1, so the output will be 0. But there's also another branch here, which goes to an AND gate. And since both of them have the value of 1, it will produce an output of 1. And we must not forget about the carry in. Since our carry in is the value of 0, we must compare the XOR value between 0 and 0. And so since our output for this one is 0, and our C in is 0, so then the output must be equals to 0. And we also have a branch into an AND gate, and so the inputs will be 0 and 0, the output will become 0. And then this one is 1 and 0, so the output will become 1. And this is true, since if you add together 0 and 1, then you'll get the value of 1, 0. But since this is only in 1 bit, so that means the sum is 0, while this one is carried into the other full adder block diagram. This is the adder and subtractor diagram. So the full adders just now are considered as a symbol right here, 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 and here. So it's 4 bits. We use the bus line so that the input can be of 4 bits, but it will be separated into each 1 bit full adder. So it's going to accept an input from A and B, but since we are considering two choices, whether A plus or A minus B, so that will be determined by this selector or the operation, where 1 is equivalent to addition and 0 is subtraction. And so the value of B is compared to the value of this operation, so that it can know whether or not to make it into a 2's complement or just a simple addition of two binary values. And the next part will show the waveform simulation. Before making the large size multiplexer, we must understand how a multiplexer works first. So right here, we have a 4x1 multiplexer, where it accepts 4 inputs and produces 1 output. And we have the selector right here with S1 and S0. And each of them are connected to AND gates. The most concise explanation is that it depends on the selector. Since it's a 4 to 1 multiplexer, then if the selector is both a value of 0, then it's going to select the first input. And if it's 0, 1, then it's going to select the second input. If it's 1, 0, then it's going to select the third input. And if it's 1, 1, it's going to select the fourth input. And we're going to implement this into the large size multiplexer for accepting inputs A and also input B. Moving on from the simple 4 to 1 multiplexer, we are going to implement the concept into a much larger multiplexer. So we're going to consider the ones just now as mux, where it will become in this form. So now we have multiple inputs that are connected to a bus line where it will divide itself into all of the different muxes. So this one is for the first least significant bit, and this one is for the next, and this is for the next, and this is for the next bit, which is the MSB bit. And each of these will consider the respective MSB bits of the inputs. As you can see here, we have the MSB bit for the first input, the MSB bit for the second, the third, and the fourth. And the selector will decide which of them to use. So for example, if my selector were to be at the value of 0, 1, then that must mean it will accept the second input. So we'll go through all of these muxes right here and select the second input, which is A1, because A1 is connected to all of the second inputs right here. And so lastly, at the output, is going to pick the value of A1 as the output. And we will show the waveform simulation to show that this is true. This is the final part, which is the register. We'll be using D flip-flops for the register. And it will accept input from the adder and subtractor and split it into 4 different D flip-flops. Each will accept 1 bit. And it will enter them parallelly and also exit them parallelly. So this is a PIPO shift register. Also to note that for the clear or the reset is inverted. So this is an active low reset switch, which means it will consider as reset whenever the value is 0. And it will continue to function as long as the value of this is 1. And since it's a D flip-flop, the output here is going to be the same as the D input, because the D flip-flops are the same as the next value of Q. So it's supposed to be the same value as whatever D is. So for example, the value here is 1, so the output here is going to be 1, and so on for the others using the D flip-flop. However, since it's a flip-flop, it will only trigger in a positive edge. And since it's also in a PIPO, which means 4 bits of output can be produced per cycle. And we can finally show the full demonstration of the ALU using the D register as the final partition.
That is all for our presentation of our ALU design, and thank you for tuning in.